CM elliptic curves. So first I begin with a brief, definition of about what CM elliptic curves are. Talk a little bit about the attached L functions, and then what we know about the p-adic nature of these L functions. Okay, so so elliptic curves are very simple-minded objects. They are defined by these kinds of squared equals to x cubed plus ax plus b, and here I have taken a and b to be rational numbers. Okay, and then but we don't want every curve that arise like this. We don't want to call them elliptic curves. Okay, we want to say that it satisfies this number minus 16 times 4a cubed plus 27b squared. Yeah, so this should not be equal to 0. Yeah, and whenever this happens, we want to say that this E is an elliptic curve. Yeah, and the delta E is called the discriminant of the elliptic curve E. All right, and so I have written down a few examples here. So the first example is y squared equals to x cubed minus x. So here we can easily plug in the values of a and b. So the value of a is -1, and the value of b equals to 0. So the discriminant is minus 16 times minus 4, and that is not equal to 0. So this will define an elliptic curve for me. And if I take y squared equals to x cubed minus x plus 1, here the value of a is -1, and the value of b is 1. So the discriminant here is minus 16 times minus 4 plus 27. So minus 4 plus 27. So that's minus 16 times 23. And that is also not equal to 0. And then the last one, I have y squared going to be an elliptic curve, because here I have a to be equal to 0, b to be equal to 0. Yeah. So we can have a more general form of elliptic curves. So this is one of the ways in which to define these elliptic curves. Okay, so what I can do is I can plot this. Say, like, yeah, for example, I can take here here I have taken y squared plus y equals to x cubed minus x. Yeah, so I'm cheating a little bit here. So on the left hand side, I don't have a square. I rather have y squared plus y. However, I can complete the left-hand side to be a perfect square. Yeah, and then I'll get this to be I can put this in a form which we have seen in which we saw in example 1. So here I have plotted the real points of the elliptic curve, by which I mean I put real values of x, and then I try to sort of see what the values of y are. Okay, so I've used the Sage to plot this one. Okay, and yeah, so this is one more example. I have here y squared equals x cubed minus x plus 1. Okay, so in the first one, we have sort of two components. We can see two disjoint components here. Okay, they are not disjoint, but yeah, we can see a picture. And in the second one, we just see one part of the component. Okay, all right. So it's kind of it's smooth. Okay, and then now just for the sake of definition, I took a and b to be rational numbers. Okay, in general, I can take any arbitrary field, okay, and then I can say that an elliptic curve will be defined by a cubic equation, okay, where the discriminant is not equal to 0. For instance, I can take there, instead of the set of rational numbers, I can take the set of complex numbers. Then I will have y squared equals to x cubed plus ax plus b, and I'm allowed to take a and b to be complex numbers. Yeah. So if I do that, then what I can do is that I'm going to get complex points for x and y. I'm going to get complex numbers, and then there is this famous theorem which says that then in that case I can there is I can view my my elliptic curve e, okay, the complex points as the C mod a lattice. C is the set of complex numbers, and it's L is a lattice inside C. So to get L, all I need is two generators of the set of complex numbers, and then I take the the free abelian group, which is generated by those two generators. And this isomorphism turns out to be a complex analytic isomorphism. Okay, so we can also say that my E is is a compact Riemann surface. Okay, and it's going to look like a torus because C mod L is a torus. Yeah. Then once I have this C mod L, this point of view of elliptic curve as C model lattice, then what I can do is that I can look at the endomorphisms of E. Yeah, so the endomorphisms of E also turn out to be isomorphic to the endomorphisms of C mod L. Okay, so when I say endomorphisms of E on the left-hand side, I mean morphisms of of E to E. Okay, um, in the category of algebraic varieties. Okay, and then they all turn out to be defined over the set of complex numbers. They are all going to be complex analytic isomorphisms, and to be isomorphic to endomorphisms of C mod L. So this is all discussed in the first course on elliptic curves. And the second one, so the endomorphisms as C mod L, it has a very nice and very clean description, as you can see. So it will be all those complex numbers mu, such that mu times the lattice L is contained inside L. Okay, so what are some special endomorphisms? So I can take all integers here. Yeah, so as I said, L is the Z span of two generators of the set of complex numbers. So in no way I can allow rational numbers or real numbers inside C, okay, to get endomorphisms, because I demand that mu L is contained inside L. Okay, so the integers are there. Okay, and when do we say that E has complex multiplication? We say that E has complex multiplication if the endomorphism ring is not equal to Z. It should properly contain Z. Okay, so whenever I have an elliptic curve defined over C with complex multiplication, then we can think of the minimal field where E is defined. Okay, so in some sense, where it is possible for us to have a field where where E has a, so to say, a model, a Weierstrass model. Okay, so then it turns out that if I want my E to be defined over an imaginary quadratic extension, then K, then this K better have class number 1. Okay, so this result is going to come from the it's going to use a little bit of hello, any questions?
This make this
Okay. Okay. So so I want my k to be to have a class number 1, and if it so happens, then my E will be defined over K. So for example, if my E has is an elliptic curve and it has got rational coefficients, it is defined over Q. And if it turns out to have a complex multiplication, then yeah, the field where this the field of complex multiplication. So this K is called the field of complex multiplication, and then the endomorphisms of E will turn out to be isomorphic to the ring of integers of K. Okay, so these things I have, and what is beautiful about these things is we are going to see. So for example, the first curve which we saw, y squared equals to x cubed minus x. Okay, so we can show that this has got complex multiplication by qi. Okay, here I is the usual imaginary number, square root of minus 1. And so once I have an elliptic curve with complex multiplication, okay, and this is defined over K, so it's important for us to assume that E is defined over the field of complex multiplication, okay. Then there is a something which is known as the main theorem of complex multiplication. This is a theorem due to many people, Shimura, Hurwitz, Doering, and so on. And then where they say that, oh, well, once I have just an elliptic curve, I'm going to get a character. So the character has its codomain in a C cross, okay, complex numbers, non-zero complex numbers, and its domain will be the Adelic group of K. Okay, so you can think of AK as the infinite product of all the completions of K. All right, you take any prime in K, and then you complete K at that prime. Okay, and then you take the infinite product. Okay, so AK star is going to be AK cross is going to be contained inside that. Okay, so it's a deep theorem. Okay, and for E given by y squared equals to x cubed minus x, I have written down this character, and it's given by at points P, which is generated by pi. Yeah, this Gothic P, if it is generated by pi, so P is a prime ideal. It's an ideal. So psi of P is equal to pi, provided pi is congruent to 1 mod 1 plus I cubed. Okay, so these things are well known. It's not very difficult to get these things. So for example, a beautiful place where this is treated is the last chapters of the book by Ireland and Rosen. Okay, so they describe these Grossencharacters in many cases. Okay, uh, so it looks like this, and then here you can ask why P is the Gothic P is equal to this prime which is generated by one element. That's because the class number of K equals to 1, and then therefore all ideals or all prime ideals are going to be principal ideals. Okay, so this is it. Now let me
Chandrakant, can you please
shift a little bit. Okay,
scroll down
so
a bit?
attached to this, once I have a character, once I have this character psi, yeah, so I can define an L function. Okay, so this character is also called the Grossencharacter. Yeah, so this is
Chandrakant, there are some
sometimes written.
comments. Can
Yes.
you just see?
Yeah, can you scroll down when you speak? Can you scroll down the slides so that we can see? I think there's. Or can you make it a full screen? If that's possible.
This is full screen.
Oh, okay. Because when you speak, I think you speak.
No, this is not in the presentation mode.
This is in presentation mode.
No.
Okay, so I'm going to share this again.
So if it is
Okay, I'm
presentation
going to
mode, then
share
you won't
this.
see the menu. The menu won't be visible if it is in presentation mode. Go to view and then say
This is in
presentation mode.
presentation mode.
Go to view and say presentation mode or something like that.
Okay, so first let me stop sharing and then, okay, I'm going to share this again. Okay, so file, view, presentation. Is this fine? Just 1 second, okay? Is this fine?
Yeah, this is fine.
Yes, yes.
Yeah, now it's fine. Yeah, now it's
Okay, okay. So yeah. So actually, this psi it factors through k star. Okay. So these things are all well known, and yeah. So once I have this Grossencharacter, we can look at, since it's going to evaluate in the set of complex numbers, I can look at psi bar, and then this will be the complex conjugate of the values of psi. Okay, and then I can take its L function, and it will be defined by an Euler product over all the primes of k. I haven't written it down explicitly, but these things are well known. Okay, and like we have L function for characters, we are saying that there are L functions for these Grossen characters. Okay, all right. Then so one striking thing about the special values of these Grossen characters, it dates back to the work of Euler, who showed that this zeta k, for zeta for the Riemann's zeta function, and then if I divide out this by 2 pi I to the power of k, so these are all rational numbers for k positive, and much later. Kummer gave a connection of these numbers with the Galois theory of q mu p over q. So if I take delta to be this Galois group of q mu p over q, and then it's going to act on the units of q mu p. So by local units, I mean those units which are congruent to 1, okay, mod p, and modulo the cyclotomic units. The cyclotomic units are, I have not defined, but these are going to be a subgroup of the group of units, and they are going to be generated by zeta to the power a minus 1 divided by zeta minus 1 and plus minus zeta to the power of b. So things like that. Okay, and then they satisfy a very good, a nice distribution property. So what Kummer saw is that these values are going to be related to the arithmetic of cyclotomic fields, and then he saw that okay, a prime number, whether a prime number p divides the class number of q mu p or not. Okay, so this is related to that, and moreover, okay, is very striking. And then he saw that if we take even integers which lie between 1 and p minus 1, then these units modulo the cyclotomic units. Okay, so on this there is going to be an action of this Galois group delta. Then we can sort of relate whether the eigenspace on which delta x by uh, by the power of this k, whether this is trivial or not, is related to whether p divides the numerator of this zeta k divided by 2 pi I raised to the power of k. So this is kind of striking. On the one hand, I have this completely analytic numbers zeta k divided by 2 pi I raised to the power k, and on the other hand, I have this completely algebraic set, which is this units modulo the cyclotomic units.
What is C naught?
Okay.
What is C naught?
Now, then, yeah, C naught is the closure of the cyclotomic units of Q mu P. It will be generated by numbers that look like zeta to the power of A minus 1 divided by zeta minus 1 and plus minus zeta to the power of some t. Yeah.
The closure in the completion of Q mu P at P, is it? So, closure in what? Closure in what do we win this thing? Closure with respect to what? Closure with respect to what?
So
closure
I have this prime P inside Q. Yeah.
Okay.
Is it okay? Can I carry on?
No, okay. You
so,
mean
so
taking
this will have
the
so
completion of
U0
Q mu
will
P at
have a
P?
p-adic topology. So these are yes, and then not at P, but the prime above P.
Take the Q mu P at the prime above P, and then take the closure of this in that. P-adic completion of the prime above P in Q mu P, and take the closure of Q C naught in that. Okay, got it. Thanks.
Yes. Is it okay?
Yeah.
Okay.
Fine.
Thanks. Okay.
Can I carry on?
Yeah, please continue, Chandrakant.
Oh, okay. Yeah. So so much later, this was given a very vast generalization by Iwasawa. So what he saw was that instead of just looking at this finite extension q mu p over q, one can instead look at this infinite tower of field extensions q mu p infinity. So q mu p infinity is obtained by by adjoining all the p power roots of unity to q. Okay, and I can take f to be any finite extension, whatever I want, which lies between f infinity and q. Okay, then I can look at this Galois group of f infinity over q. Okay, and then I call this gamma. So this will be isomorphic to zp star. And again, I can do the same trick. Okay, but now I will have u infinity, and then I have c infinity. Okay, so so u infinity will be sort of the projective limit of all the units of of all the possible subfields of f infinity over f, and then c infinity will be the corresponding cyclotomic units there. Then one can show that this gamma, okay, which is this Galois group of f infinity over q, is going to act on u infinity modulo again, the closure of c infinity. Then what he showed is very, very precise. I mean, what he sort of thought should happen is a very precise statement, which is known as the which will be ultimately related to the main conjecture of Iwasawa theory for these fields f infinity. And what he sort of saw is that the structure of u infinity mod c infinity bar. So it's about this module. So he saw that u infinity mod c infinity bar, this is going to be torsion as a module over gamma. Okay, so as a gamma module, it is going to be torsion. So as a distortion, it will have an any highlighter, and then he saw that any highlighter will have will be related to those through something which is known as the p-adic L function. And then what is this p-adic L function? This p-adic L function, they are going to interpolate the special values of the of the zeta k, which we saw earlier. Yeah, just a while ago we saw these values, zeta k mod 2 pi I raised to the power of k, and then the p-adic L functions of Kubota and Leopold are going to be related to that. So this is sort of something which we saw. So what I have written here is not very precise, but it's just to give you an idea of what is this about the structure. Okay, and then the structure, the module on the left hand side will later be related to class groups. Okay, and then that becomes those class groups defined over this infinite extension will turn out to be related to these p-adic L functions of Kubota Leopold, and that's the main conjecture of Iwasawa theory, which was proven by Mazur and Wiles. Okay, so this is something intermediate between that Mazur Wiles story. Okay, so now what? Now, Coates and Wiles later on saw that instead of taking p power roots of unity, what about I take p torsion points of elliptic curve, or pi torsion points of elliptic curve. Remember, pi is generator of a prime ideal p. Okay, so that's what I meant by this elliptic analog of Kummer's theorem. Yeah, so Kummer could relate the structure of certain Galois objects with the special values of L functions. Okay, and what were they interested in? That they want to have this elliptic analog precisely because they want to use it to prove part of the conjecture of Burton-Newton-Dyer for elliptic curves with complex multiplication. Yeah, so with this question in mind, they started to think about whether elliptic analogs of Iwasawa's this generalization of Kummer's theorem is valid or not. So this was done by Coates and Wiles, okay, in an inventionist paper. About now, so everything is for CM elliptic curve. So for that, they need K to be an imaginary quadratic field with class number 1. Okay, I'm anticipating that I'm going to have an elliptic curve defined over K, and then I'm going to take O to be the ring of the psi is the Grossencharacter of E div prime is very important for the method of Coates and Wiles to work. I don't think that so far this is known. In the case when P is inert, I don't think it is known. I don't even think if p-adic L functions have been constructed when P is when P splits as when P is ramified in OK, okay, in the or inert in OK, and the pi is yeah. So my pi is going to be in the endomorphisms of E. So which means that I have a map from E to E, which is given by multiplication by pi. So once I have this multiplication by pi map from E to E, I can look at the kernel of this map. All right. So we have to remember that K has got class number 1. So I'm in this setup throughout. okay, and O denotes the ring of integers of K. So here I have written, I think, OK also, so but O. And then it has attached to the elliptic curve, I have a Grossencharacter. So this setup is going to be very important. This is the setup in which they work, and then the prime P splits in OK. Then another important module which they work, okay, is this Y infinity. Y infinity will be a generalization of the units of the local units modulo the cyclotomic units. Okay, so just to go through about briefly. So e pi to the power of n+1 denotes all the pi to the power n+1 torsion points of E. And then I adjoin these points to my base field K. Okay, then I get a field extension called Fn, and one can even show that the prime P, okay, is totally ramified in Fn. And in fact, one of P and P bar is totally ramified in Fn, and I'm taking P to be the one, I'm writing P for the one which is totally ramified in Fn. And phi n denotes the completion of Fn at Pn. Okay, and Un are the local units which are congruent to 1 mod Pn. And again, I'm coming up the units for the field Fn.
Hello, Chandrakant, can you hear us?
I'm coming up the units for the field Fn units. For that, hello.
Yes, we can hear. We can
Any
hear.
questions?
No. Continue. Yeah, we can hear.
Okay. Okay. So it's a bit technical for me to define what elliptic units are. Okay, but they are going to be defined on um, by taking a Weierstrass model for E, and I'm going to look at the x coordinate of certain points, okay, and it's going to be defined relative to an ideal inside O. Okay, so let me just leave this definition for a while. Okay, but these are certain analogs of the cyclotomic units. And then I can look at the field F0. F0 is nothing but the field which is obtained by attaching just the pi torsion point of E to K. All right. And then this is going to be a Galois extension of K. And then I look at this Galois group G0. Yeah. And then it's going to act on this on the pi torsion points, and then it's going to give me a character. Okay, so in fact it gives us a character inside O pi star, but because my P is totally split, it is going to be isomorphic to ZP star. So I can think of a character having values inside ZP star. Yeah. So under this action, so once I have this action of this group G0, I can decompose my this quotient UN mod CN bar. Okay. So depending upon how G0x. Okay. So by UN mod CN bar I denote the eigenspace where G0x by x via chi to the power of I. Okay, then again, so let's go up the tower, this tower of pi torsion points of E. And then if I do that, I'm calling the field extension, which is obtained by attaching all the pi to the power of n torsion points of the elliptic curve to be F infinity. And as before, I'm calling gamma to be the Galois group of F infinity over F0. Then again, as before, yeah, I take the projective limit of all these units modulo elliptic units, okay, with the respective action. of 0. Okay, so this is the setup in which Coates and Wiles worked. Okay, so let me also say that on the module y infinity, there is an action of gamma. Okay, and then with that action of gamma, I can convert y0, y infinity to be a module over this algebra, Iwasawa algebra. Okay, so what is this algebra? So this is defined by ZP and then a power series in gamma, and it is going to be isomorphic to ZP power series in one variable. Okay, so to show that ZP gamma is isomorphic to ZP, so this is pretty well known. So we have to use something known as Mahler's transform. Okay. And then this is going to be true even if I have not just one gamma, but say gamma 1 cross gamma 2, then I will have ZP, say T1 comma T2. Yeah, so this gamma Mahler's transform, and then gamma transform will give us all this isomorphism between these completed group rings and then Iwasawa algebras. And then how does gamma act? Okay, in relation to what T does on elements of y infinity, the I component, okay, is given by this equality. We say that 1 plus T acting on y is given by the action of gamma naught on y. Okay, gamma naught is a generator of this gamma, a topological generator of gamma. Okay. All right. So now what? Now let me give you one more input which is needed, which is that this theorem of Damarell. Okay, so Hurwitz, Bertsons, Newton, Dyer, they all proved this in special instances, and then Damarell also proved, okay, that these numbers, the L function of psi bar raised to the power of k evaluated at k, divided by some kind of a period. Okay, this omega is going to be an analog of the of 2 pi I. They are all numbers inside k. They all belong to k. Yeah. So once they're inside k, I can view these numbers as being in the completion kp. Okay. So this is a theorem, a deep theorem due to Damarell. So it's not so easy to prove this. Okay, so once I have this, these numbers were shown, okay, to be p-adically interpolated. Okay, let me explain to you what it means. So this is a construction due to Katz and Manin-Vishik. Manin-Vishik did it in a more special case, and then Katz did it in a more general case. So what happens is that if I take a non-zero residue class. Okay, so it means that I is not congruent to 0 mod p minus 1, and I take u to be 1 plus p. Then what it says is that there exists a power series, okay, in one variable. Okay, so gi evaluated at u to the power of k minus 1. Okay, so up to some factors, this is going to be related to the L function of the Grossencharacter. Okay, and I can put here, and this is going to be true for all k with k congruent to I mod p minus 1. Okay, so pay attention to this non-zero residue class I mod p minus 1. Okay, so this is a theorem due to Manin-Vishik and then Katz. This is a very deep theorem. And so Manin-Vishik first constructed this p-adic L functions for in fact for modular forms, and then they later did this for modular forms with complex multiplication. Okay, u is 1 plus p, so and this I've said, and then So here's the main theorem of Cotes and Wiles. So again, the same setup as before. I have P to be a prime of good reduction for E, by which I mean that the reduction of E is, if I look at E as, if I take the reduction of E, okay, over a finite field, this FP, then E should still be an elliptic curve. Then for its I not congruent to 0 mod P minus 1, not congruent to 0 mod P minus 1, then in that case, I have this, I have I have this this isomorphism. Y infinity I is isomorphic to lambda mod GI of T. Okay, so GI of T is a new power series, okay, and it's related to the one which was constructed by Manin, Vishik, and then Katz. Okay, just with a difference in some coefficients, but one can up to those coefficients one can have this isomorphism. And this appeared in a paper in 1978. This appeared after this work of Cotes and Wiles, which I quoted just a while ago, their inventionist paper. And so this is an isomorphism, and then there are some other conditions as stated, in the paper. There are some conditions, but they all can be removed. There is not much of a problem in trying to remove that. So I have seen versions of this theorem being quoted even when those conditions are not satisfied, but they're all those cases concerning anomalous primes, and then they can be easily dealt with. Okay, so this is that for its I, which is not congruent to 0 mod P minus 1, I have this isomorphism. So now this is the question. What happens in the case I is congruent to 0 mod P minus 1? Okay, so this is the case in which I'm interested. Okay, so we have to know this branch, this y0 with a trivial action of chi. I have to know this part also if I have to know the full structure of y infinity over f0. Okay, then the question is, does the proof of the theorem go through in this case without any difficulty? Okay, so there are two instances where this is mentioned in the paper of Cotes and Wiles. So the first thing they mention is in the introduction. They say that this is highly non-interesting, and maybe different techniques will have to be needed for this. And in fact, in the paper, it's written that later, so in the paper, it's written that the proof of one of the key theorems, okay, so is more difficult in this case. So, so this is what we want to understand. What is this difficulty? And so this is about the existence of certain power series. Okay, in today's time, we can say that an analog of a Coleman power series is hard to get in this case. In the case I is congruent to 0 mod P minus 1, though this terminology Coleman power series does not seem to have existed at that time, but nowadays, I mean, this is there, and then it seems that it's difficult to get this power series. Okay, and the other thing is that this is the problem that they are saying difficult is a completely local problem. Okay, so let me just give you a sense of what it is. So it is that this there is a module called x infinity I, and then for more details you can look up in the paper. And then so this is defined analogously as the y infinity. However, I'm taking only some kinds of special units here, un prime mod un prime raised to the power of p. Okay, so I'm not going to define this precisely. but yeah. And what is the structure in this case? What is the structure in the case when I is congruent to 0 mod p minus 1? Okay, so this structure they could not determine in the case I is congruent to 0 mod p minus 1, and hence the difficulty. And why is it that one is not possible to determine the structure? It's because to determine this the structure of x infinity I as a module over the Iwasawa algebra, okay, they relied on an earlier result of Coates and Wiles, which was in their earlier paper, in their inventionist paper. They use a result there, okay, to get to the structure of this x infinity I. So if at all one has to, if we want to, you know, somehow go around this difficulty, one has to give up this relying on this earlier result of Coates and Wiles, okay. And I spoke to John Coates about this. I asked this question, what he thought about this, and then he seemed to have some ideas regarding, you know, existence of some Euler systems and things like that. But I want to just present one approach where this turns out to be, you know, I mean, much more direct. So, but at the cost of extending, you know, working over a much bigger field extension. So our idea is as follows. So instead of just sticking to
Hello, Chandrakant, are you there? I think video is stuck.
Yeah, video, audio, both are stuck. So
maybe I think his signal.
I think he's lost the connection also. It's showing the connection.
maybe he'll rejoin.
I think he'll rejoin us.
I think he's lost the connection. That was the reason. He was...
I think he's probably trying, so we'll just wait for a moment.
So we try to work over this full p torsion points of the elliptic curve,
yeah, maybe
and not just the pi torsion points. Okay. So this has been the structure of the module over this much bigger extension has been studied by Yager, one of I mean Coates' own students, okay, but over an Iwasawa algebra of 2. So morally, one is saying that this field, the k e p infinity over f0, that will be an Iwasawa algebra that will be an extension of dimension 2. Okay, so it will look like ZP direct sum ZP, and I take this algebra in two variables, which I have denoted here by lambda 2. Okay, so lambda 2 will be a power series ring in two variables. Okay, with coefficients coming from ZP. Yeah. So, and the structure of this, and I can look at, you know, x infinity again here in this setup. So at this calligraphic x infinity here. Yeah. So I'm going over to a bigger, much a bigger extension, and then this has been studied by Yager. Okay, and then he tried to relate this to another two variable p-adic L function constructed by Katz. Okay, and and we're going to use this one. So for this to be able to use this, so here is the basic setup. Okay, as before, I take So I'm going to use this bold, U infinity. So this will denote the local units which are congruent to 1, okay? But over this extension, ke p to the power of n plus 1, okay? And U infinity as before remains the group of principal units over this Fn, okay? And this was the ke pi to the power of n plus 1, okay? And what one can show is that if I use, class field theory, local class field theory, one can show that the norm map from U infinity to this bold U infinity to U infinity is a surjective map. So this is the first thing which I observed, okay? And then the second thing is that if I look at the action of delta on U infinity, then delta is the Galois group of. So I think earlier I denoted this by G0. I don't know why I'm using this this notation delta. I should have used G0. So this is the Galois group of F0 over K. Then this module U infinity decomposes as this into eigen-components. And then Yager showed that the trivial eigen-component is isomorphic to lambda 2 itself, which is this Iwasawa algebra in 2 variables. Okay, so we'll use these 2 inputs. Okay, by the way, this is Yager's theorem. It's very nice theorem, and it says that if I take 2 integers I1, I2, which are modulo p minus 1, then I will have power series in 2 variables, okay, such that my y infinity, but over I'm looking at now at y infinity over this much bigger extension, not just ke pi infinity, but ke p infinity, all right? And so he showed that this has a very nice structure and is isomorphic to this calligraphic H modulo G, I1, I2, and then ST. So, so here calligraphic H is, so in this case, it will turn out that this is isomorphic to power series ring in 2 variables, okay? And H is some explicit factor which I have not written down. So basically, y infinity I1, I2 is isomorphic to Iwasawa algebra in 2 variables, modulo and ideal, which is generated by this G. Okay, so this is what Iwasawa Iwasawa's results would have predicted. Then, so this is the key theorem which we proved. Okay, so so I can get this this commutative diagram. Okay, so in this commutative diagram, what are the objects? So I have this lambda 2, which is power series ring in 2 variables, and then I have this U infinity 1, which is the component which I'm interested in, and I have this surjective map from U infinity 1 to U infinity by the norm map, and on the left hand side, the vertical map, I have this a canonical map from lambda 2 to ZP power series in 1 variable, where I just substitute S to be equal to 0. Okay, so I'm just projecting it. Then I can show that this map is this diagram is commutative, and the proof uses in fact, one crucial input came from one of the results of Coase and Wiles in their earlier inventionist paper. So this is the key theorem, and then with this surjectivity, one can show that this diagram is commutative. Okay, so now, so what can I say? So now, if I go back and then I look at the principal the power series which interpolates the special values of the L functions, which was constructed by Yager and Katz. Okay, then one can show that here. I can show that. I have removed that, yeah, by specializing, I can show that we do have an analog of Coase and Wiles theorem for the trivial eigencomponent. Yeah, so that's what I have written, that as power series ring in one variable, we have this isomorphism. Okay, so this is on the left hand side, we do have this trivial eigencomponent, and on the right hand side, I have this ZP power string in one variable modulo the a certain p-adic L function, calligraphic G and script G. Yeah, so they generate the same power series in ZP unramified and in one variable. Yeah, so this I mean solves that the problem regarding the missing eigenspace in the result of Coase and Wiles. I would like to thank all of you for your attention, and I'm sorry for the technical glitches.
Yeah. And thank you, Chandrakant.
Yeah, thank you so much.
Yeah. So any questions? Maybe Tanvi can.
Yeah. Any questions?
So,
Yeah, Somnath probably has a question.
Okay.
yeah, so maybe Chandrakant,
Hi, Somnath.
hi. So maybe I missed the. So hypothesis was, so you did it for the primes which do not split, and also for p equal to 0 mod p minus 1, or
No. I'm taking an ordinary prime, so it still splits. Yeah.
but you made some remark about split and non-split, right? So
yeah,
you
so
are
I made
still
a
in the
remark
split
because
case?
when I asked John Coates, he said that in the super singular case, he doesn't know how to construct p-adic L function for CM elliptic curves over the full p torsion points. Yeah, I think so. So, I mean, even for the statement of this this Coase and Wiles theorem to make sense, I think what he meant was that we will need p-adic L functions, and that is not known in that case.
And this
So the
whole
improvement is only for the I congruent to 0 mod p minus 1.
Yeah. That I understood, but and this, yeah, I mean, still, I mean, maybe, yeah. So this going to two variable, I still need to understand sort of this Yager's. Yeah, maybe.
Yeah. So in fact, I will. I mean, yeah, if I had a little bit more time, I could have given a sketch of the proof. So we need to know that the prime p or the prime pi is totally ramified in that extension. I mean, my interest was in trying to get to the cyclotomic line where p is also totally ramified, and I was looking at other totally ramified cases, which will allow me to study this case more, and then I was hoping that I can say more about the Iwasawa mu invariant over the cyclotomic this extension. And so that led to this looking at this two variable, but the case in which I was interested was not covered by this theorem. So I just thought maybe I should better look at this.
Yes. Okay, thank you.
Any more questions? So if there are no more, let's thank the speaker.